you really should consider investing in visibility so that you have the data to work with, even if it costs a little bit of performance. How do we ensure that people who are not performance engineers with a capital P and a capital E, right? Like, how do we make sure that developers have access to profiling so that they can see what lines of code are the most expensive? That kind of making accessible of the performance data makes people make the right decisions, because people aren't going seeking out to do a bad job or waste CPU. They just don't know what they don't know.
Hello, I'm Martin Thwaites.
And I'm Jessica Kerr.
And you're listening to o11ycast, or o11ycast for short. A monthly series where we talk about how we can make production systems more observable, more reliable, and easy to maintain. o11ycast is brought to you by Heavybit, the leading investor in developer-first startups. For more information, visit heavybit.com.
If you're interested in being a guest on this show, or if you have a specific topic you'd like us to dive into, you can reach us on Twitter at o11ycast. That's at o11ycast.
And it turns out that there is a certain satisfaction in making a line go up or making a line go down. So this is one of those things where you're just always curious, how hard can I push it, right? Like, it's similar to how people are like, how hard can I floor my performance car, right? Like, you're not necessarily a race car driver, but it still is interesting to figure out, like, how fast does my car go if I really push the limits? What can I do to kind of tweak it and improve it? And yeah, sometimes I've been told off for, oh, we don't need to make that optimization right now. Why are you worrying about this? But yeah, basically this innate curiosity about how do I kind of explore all the nooks and crannies? How do I squeeze every drop of performance that I can get? And sometimes it can seem a little bit pointless and tedious, but it turns out every 0.5 or 1 or 2% really, really adds up if you keep on doing it for a long period of time. So that's how I got into this.
It kind of gets a bit addictive, I think, doesn't it? You can kind of get a little bit intoxicated by those little small additions on that graph that you just a little bit more.
Yeah, it's the feedback loop, right? Like, it's absolutely the feedback loop. And we talk a lot on o11ycast about kind of feedback loops and how engineers get dopamine hits from seeing their stuff go out live. In my case, it's not necessarily, seeing the users use the feature so much as the immediate dopamine hit of, I've just paid off my salary for this year, right? Like, that's kind of really cool to be able to justify the cost of your headcount.
Strictly by saving us money on AWS?
Yep.
Yeah, I think there's some times that I've heard you talk about the nanoseconds that we've saved in a Lambda somewhere, and then you go, oh, that doesn't seem like much, and then you tell us the cost of what that is, and you go, okay.
Yep. It turns out that shaving, 100 nanoseconds off of a call that gets invoked billions of times per day, yeah, that kind of adds up. The trick is figuring out what's the tight loop and what is kind of something that is not the performance critical section.
Oh, so if you pick the right line and you make that line go down, you're accomplishing something.
Yeah, exactly. But if you're picking a different line and it's something that isn't actually all that significant or important, then, it's an interesting brain snipe, right? Like, it's a nerd snipe, but it doesn't necessarily make a dent in the bottom line.
Great.
There's actually this cool challenge going around as we're recording this called the 1 billion line challenge, where you're supposed to aggregate a bunch of weather station temperature measurements and do it as fast as possible. And, that's the kind of cool stuff that people who are interested in this general field like to do.
Yeah, it started in Java. Some of the Java people were putting together the 1 billion row challenge to see how fast you can parse 1 billion rows and aggregate data over 1 billion rows, which is a really interesting challenge that they did after the festive period. Maybe before the festive period would have been a better time to do that, and everybody could have been nerd sniped over Christmas. I love those kind of challenges where I've been looking at some of the solutions and they're doing little things like they're moving bits and going really into moving the actual bit value instead of doing addition to make it quicker. And I feel like there's a point where you get to that actually that is way too addictive, that you can get way too low. You can be recompiling kernels to try and make it go faster.
But it's only too much if you're only going to run it once. When you're a SaaS company and you're supplying this billion times a second or billion times some time period, Lambda to hundreds and thousands of other companies, then a little bit of performance improvement really matters.
Yeah, and it definitely used to be the case, right? That you had developer time being relatively expensive. It used to be that you could say, this will slow our engineers down by, an hour every month that we have to think about it. Let's just, let those servers burn. That doesn't necessarily fly anymore. Both developer time and your AWS bill have now become very, very expensive resources that you want to carefully optimize as companies are thinking a lot more about profitability, about their rate of cash burn, and so forth.
Yeah, the idea of auto-scaling and let's get auto-scaling really in so we can scale down to one server rather than 10. And then you work out that actually it's only going to cost us $2,000 a month to run at 10 servers all the time. And that becomes I'll just get the developers to do other things because it's way cheaper than them spending 3 months trying to make auto-scaling work and save $9,000. Wow, that's not anything compared to what we're going to be paying them in salaries for that amount of time.
Okay, so the trick here is knowing what that amount is and knowing whether this is a line you should optimize. And I really want to get into how do you find that line, how do you get it, and how do you know which one? But first, I know a lot of people who listen to OllieCast already know who Liz is, but that is not everybody. Liz, would you introduce yourself?
Hi, I'm Liz Fong-Jones. I'm the field CTO at Honeycomb, working in the office of the CTO with Charity Majors, and I am a former member of the DevRel team at Honeycomb.
And before that?
In past lives, I was a site reliability engineer at Google, and I worked with some of the most awesome brands that were using GCP to help them adopt SRE practices. And as I was alluding to earlier, I've always had an interest in performance engineering and figuring out how to tweak my capacity to be as efficient and lean as possible.
So at Honeycomb, in addition to many other things, Liz does a lot of optimization of our infrastructure on Kubernetes.
Yeah, it's definitely been a fun little challenge to keep our cost of goods sold to a minimum so that we can enable spending that money on delivering innovative new features, on paying our developers to continue to develop new features. And it's kind of just this ongoing exercise where we are always striving to help our customers get quick access to data. I think that's kind of one of the other aspects of optimization that's overlooked often, is that sometimes it's about the dollars, and sometimes it's actually about the latency that you serve to your customers, right? That you have.
Faster and cheaper come together.
Yeah, exactly. If you're billed by the Lambda second, every second that you save both saves the customer waiting for the results of the Lambda, and it also results in a lower bill.
So y'all were talking about a billion row challenge, and at Honeycomb, that's like every second when someone runs a query, our thing is querying an unreasonable amount of data live when you ask it and getting the results back in an unreasonably fast amount of time. And that takes a lot of compute. And then that compute is expensive. And so a lot of our special sauce is making that not too expensive.
Do you think that is the Lambda equation has changed how we think about it? Because before, when we were thinking about servers, we think about, when we've rented a server off AWS and it's got 4 CPUs in it, we should actually use all 4 CPUs. We don't care if we only end up using one of those CPUs. Well, fine, I don't care. I want all the CPUs to be used. But when you're charged by the millisecond, do you think that's changed how we think about performance engineering?
Yes, it absolutely does influence that, and in ways that you don't necessarily anticipate. For instance, if you have a server that is on and running all the time, you can keep your TLS connections warm, right? You can keep a WebSocket or you can keep a gRPC connection open to whatever servers you need to connect to. If you have a Lambda that AWS is freezing and unfreezing, and it could go minutes between requests, or it could wake up, 5 milliseconds later and run another request, that Lambda has to restart its connections to all of the other backend services like AWS S3 that it needs to talk to. And that can add up to a surprising amount. So one of the funny things that we had to do is we had to cache the certificate, the SSL certificate for s3.amazonaws.com. And we had to just say, hash the certificate. If I've seen it before, I don't need to verify that it's still a valid certificate. Because you wind up running those setup and teardown processes so often. So it's not just about trimming seconds out of your core compute loop. It's also about thinking, what do I need to do to set up and tear down, and how do I make that as efficient as possible versus if you're running something steady state. So there are a lot of different trade-offs. But I think, Martin, the thing you are alluding to is actually one of the reasons that we switched to Kubernetes. Honeycomb, for a very long time, was a EC2 only shop with the use of Lambda for querying backend. But we discovered that we are leaving a lot of performance and capacity on the table because even with auto-scaling and scaling each individual service separately, we were not bin packing things onto machines. And there would be periods of time where we could interleave workloads on that same machine, and we weren't availing ourselves of it because each pool of workers was its own dedicated set of EC2 hosts. So I think definitely that desire to push capacity higher was an important side effect of our transition to Kubernetes. The actual real motivation behind our transition to Kubernetes, though, was the ability to handle deployments more easily. That it turns out our janky system of kind of rolling out via cron jobs on our EC2 hosts really needed to be replaced with more stateful deployment sets and so forth with Kubernetes. And we just decided, hey, we're not going to segregate these workloads anymore. Kubernetes lets us not have to worry about it. It's just all generically CPU.
I think that alludes to that idea that we waited at Honeycomb to the point where it became a problem, that it was cost effective for us to skill people up on Kubernetes, understand what the Kubernetes paradigm was in terms of scaling and performance and all of that kind of stuff.
It also got cheaper over time because the number of people with Kubernetes experience coming in from the outside was much, much, and much higher the longer we waited, right? That, in 2016, 2017, it would not have been reasonable to expect, anyone that you interviewed for a SRE or core services job to understand Kubernetes. And now it kind of is this thing that most people in our area of the world have some exposure to.
That's a great point.
Not all. And I think that's kind of that, tipping point of at what point does something kind of have traction? At what point does it become the default? And I think that brings us nicely to the subject of cognitive load, right? Like that is a cost as well, right? Managing technology choices, managing code complexity. Like I'm not going to write in hand assembly something that is frequently modified, no matter how performance critical it is, because you might value the ability to iterate on that code a lot more than spending an extra, $1,000 or $2,000 or even $5,000 a month on.
On the other hand, you tend to come back to code that's very stable and runs a zillion trillion times a second, and then you performance optimize it.
Yeah, exactly. So I think that goes to how do you pick what to work on, right?
Yeah, how do you choose the right line to min-max?
And I think that's not even picking the right line. I think it starts with this kind of global perspective, right? You have to zoom out and look at my entire AWS bill, and then you have to look at, okay, what elements of your AWS bill are the most expensive? If it's your RDS, there's no need to hand optimize your application code, right? That's a case for, okay, we should, maybe look at Aurora, or maybe we should look at the Graviton instance types for RDS, right? Like there are different control knobs for each AWS service, only some of which relate to your application code. But supposing that you look at it and it's indeed, your EC2 instances or your Lambdas, at that point, you then have to figure out, okay, what are these instances majority being used for? In some cases, it is idle capacity. In some cases, it's one or two applications. Or in some cases, it may just be a mixture of different applications that are kind of all consuming that quota of that particular service.
You mentioned it might be idle capacity, and Kubernetes helps with that.
It can help with that. The challenge is you have to have a mixture of different workload sizes, which is possible to do at a large company that has, hundreds of different microservices, each of which have kind of their own different capacity scalings. But if you're a company like Honeycomb that has macro services, where we have maybe a dozen different kinds of microservices, each of which are very, very horizontally scaled, you suddenly don't have this kind of heterogeneity of workloads, right? Just think about things like, can I bin pack onto this machine what's the most common combination of my top 2 or 3 workloads that I expect to see, and to size things accordingly? So for instance, if you have a machine that has 32 cores available, You want one core allocated for, various maintenance tasks, daemon sets, the hotel collector, right? So that leaves you 31 CPU to work with. If you have jobs that are 17 CPU each, you're never going to be able to squeeze 2 of them onto the same machine.
Oh, that's a lot of CPUs in one job.
Right, so that might waste a significant fraction of your capacity. If all you have is 17 CPU jobs, then you're going to be wasting, 14 CPU, right? Unless you have something that can plug that 14 CPU hole. So in general, we find it's best to make sure that every job is no more than half minus 1 CPU of your smallest machine size. And also, it's important to have, for the much, much smaller jobs, to be able to fit 2 or 3 of them in there, right? So let's suppose that you had, a 15 CPU job, and then you had some 5 CPU jobs, right? So you can squeeze a 15 and then a 5 and a 5 and a 5 to make up 30, which is close enough to fully utilizing the machine, right? So Kubernetes makes it possible to squeeze those workloads together, but it doesn't guarantee that there will be zero wastage. It's kind of on you to size your jobs appropriately. And Jess, I 100% agree with you that, 15 CPU, 17 CPU, that's a lot of CPU. But if you have shared caches that are maintained in memory that are used by all 15 of those cores, you don't want to be populating 3 separate caches across, 5 CPU jobs, right? You'd rather have those all in one thing that's talking to the database one time to refresh its memory. So it's kind of this trade-off of how much work do I wind up doing populating things that are shared versus how much work is feasible to kind of multiplex and kind of scale out vertically within a job. So there are kind of all of these interesting challenges that you have to keep an eye on and see, where am I underutilizing, where am I overutilizing, kind of how am I sizing things, and are the kind of Kubernetes automated processes working correctly?
So this is an observability podcast. Therefore, I'm going to ask you, how do you find out how many CPUs each job is using and requires? How much memory is being shared in these shared caches that are valuable enough that we want to keep all the CPUs busy sharing them? How do you find out about these things?
So it's important if you have any kind of shared in-memory data structures where you're evicting things from cache, right? Like you want to have telemetry about the size of the cache, how often you're evicting things. You also need to keep kind of pod level, node level statistics, and that's where the OpenTelemetry collector running the node metrics modules can really help for gathering information on what pods are running on the current host. And that's where having, the OTel collector as part of your daemon set that's running on every single node can really populate and fill in the details about, how much are you reserving and how much are you actually using. But it doesn't give you a breakdown by which specific area of memory. It just says this one pod is using this much memory.
Right. So if you want to know the size of your cache, you're going to have to emit that yourself.
Yeah.
Because your application knows how much memory, or can know how much it's using for this particular purpose. I want to clarify a couple terms. When you said a computer with 32 CPUs on it, in Kubernetes, that means a node, right?
Yes, one individual kubelet.
Kubelet is the process that runs on the node computer in order to make it into a Kubernetes node, right?
That's correct. The kubelet is kind of the scheduler and resource manager of everything that's running on that individual VM or physical server that turns it into a Kubernetes node.
Yes. And on a Kubernetes node, you can run a daemon set. Well, specifically, if you run a daemon set in Kubernetes, then you get one job, it's a pod, one pod per node, and it can do the tracky things per node, which means per computer. So you can get the information about that physical infrastructure.
Yes, exactly. So people use that for monitoring, people use that for telemetry forwarding and processing, people use that for emitting logging, and people use it for security purposes if people have some kind of security monitoring job that they want to attach to every single Kubernetes node.
And Martin, I believe you advise people to send their application telemetry to the collector running as a daemon set on the node, right?
Correct, yeah. So if you've got things running on there, you use the node IP, which means that it doesn't go through the software networking and there's no chance of it transferring software networking between multiple nodes and all of that kind of stuff.
And then you are crossing availability zones, maybe using a load balancer, right? Like, I think this goes to the question of what are you optimizing for? Sure, it might be in some world more efficient to have a centralized fleet of OTel collectors via a load balancer, but now you're trading off the inefficiency of having CPU dedicated to your OTel collector on each node for now I am guaranteed going to be crossing network and crossing a load balancer and paying for all of that network traffic. So it's kind of a situation where networking often, we have found, can be more expensive than the cost of the compute itself for a highly optimized compute job that is handling lots of data.
Oh, okay. So if you optimize your compute in a way that hides a bunch of networking costs, you could lose.
Yes, exactly, right? Like imagine that, oh my God, like I can run only one OTel collector and, maybe it scales to 3 and then it scales back into 1, at night. I've just saved a bunch of money on my compute, but now I have this problem. And I have this problem that everything needs to cross to a different machine, maybe even cross to a different availability zone. So I'm getting billed a different way.
So in Kubernetes, you typically run multiple nodes, like usually at least 3. And for high availability, you want those nodes in different availability zones. And now in AWS, there are multiple availability zones in each region. So you're in the same AWS region, but this cross availability zone traffic costs you money.
A lot of it.
Even within the same region.
Yes. And that's true across all cloud providers. It's not just an AWS thing. There is a real cost to, digging fibers to go between different buildings on the same campus or, even different campuses in the same city. Like that does cost money. I understand why they charge for it.
And it takes time. So again, faster is also cheaper.
One of the interesting things I was talking with a customer, I think it was last year, about they'd made a decision that their entire ecosystem was cross-region. So an order service in availability zone A in region 1 could be communicating with the email service in the availability zone B in region 2. Everything was 100% cross-region. And from a telemetry point of view, that's a nightmare if you think about things like tracing, because trying to get all of that into one place so you can do things like sampling and all of that kind of stuff, they'd optimized their compute so that they had full reliability. Everything could go between all the different regions. They could lose an entire region or part of a region or a service in a region or an availability zone in a region.
Right, because they were running active. So it, didn't matter. They didn't care which availability zone they were talking to.
Exactly.
Because they had 2 active availability zones at all times?
Well, they had 6.
Oh, 6. I was close.
Yeah, so normally in my opinion, a sane person would have 3 availability zones running.
In the same region?
In the same region. And they would scope it to that particular region. A request would live inside of that particular region. But they were doing it across multiple, and they had reasons for it. The problem was that the costs then went up because, yes, we talk about cross-availability zone costs being high. Cross-region costs are even higher.
Yeah, and it's fine even to run active as long as you default to your own region and you default to your own availability zone. You only communicate across if you have no other option, right? But again, this is a thing where if you don't have the data to understand what your architecture is costing you, you have no idea, right? Like you're just saying, oh, I want to maximize reliability. Let's just, round robin it and talk to any available host, right?
Yeah. As a developer, like what I love about Kubernetes is the abstraction, is that I don't have to understand servers. I can just understand deployments and I can describe how many of my service at least should be running somewhere and I don't have to worry about where.
And you shouldn't have to worry about it, right? I think that's kind of why you have people like myself or Lex from our SRE team that kind of go and look at our infrastructure afterwards. And then we say, okay, this is starting to tick up. We have to look at this now, right? We have to revisit it. You don't have to prematurely optimize things as long as you have sensible defaults for people and you're kind of catching any issues that are coming up and increasing the cost that are not expected.
Nice. Okay, so your strategy with capacity and performance optimizations is to let developers do what they do and then come back and clean up after them.
Not so much clean up as like if something winds up being more expensive than we expect, then that's an experiment that we then go and say, okay, like let's do that, but differently.
So it's react to problems instead of preventing them.
Yeah, because if you try to prevent everyone from spending any AWS money, right, like that's how you get really restrictive change controls. That's how you get shadow IT. So it's much better to kind of, within bounds, let people spend up to, $5,000 or $10,000 a month. And if people wind up costing more than that, then we'll see what we can do to help them achieve the same result, but for cheaper.
So do you have any advice for people on how to then forward educate people so that the same problem doesn't happen? Because obviously these are recurrent problems. What can people do to try and make it better? Is it just observability?
Yeah, it's the feedback loop. It's looking at the performance of the thing that you're deploying and the cost of the thing that you're deploying. So tagging which service is responsible for what is crucial. And that's why, let's say that we've solved the bin packing problem, right? We don't have a bunch of unallocated wasted space. And let's suppose that we've solved the problem of growing and shrinking our pool of nodes. So at that point, we start looking at, okay, out of the CPU that you're consuming, right, let's go ahead and take a profiler to it, or let's go ahead and figure out what we can do to balance the load better so that you don't have one node that's sitting 10% utilized and one node that's sitting, 120% utilized, right? So it's kind of challenging because there are so many different ways that you can have issues. You kind of teach people to recognize some of the patterns and which tools to apply, but you're still relying upon them to look at the signal. You're still relying on them to kind of pattern match and say, okay, this looks like a thing that I've seen before. I know what to do because, Lex or Liz showed me, or Dean showed me how to deal with this situation.
Yeah, I think this just comes down to people actually caring about it a little bit. They have lots and lots and lots and lots and lots of things to care about. This is just one extra thing.
And if they have easy access to that information, it's a lot easier to care.
Yeah, that's why kind of democratizing access to data, at least read-only, is so important. This is why we so firmly believe in with the DevOps and Agile movements that, when you shift things left, when you make it easier for people to see themselves what's going on rather than handing off to another team, they tend to kind of take responsibility and ownership of it.
It's interesting that the shifting left here is shifting left of visibility and awareness. And the accountability happens naturally then.
Yeah, exactly. Like people used to in the past, when they were hiring people, when you're hiring 10 people a week, it was like, whatever, the cost of machines doesn't really matter, right? Like we need to onboard these people, we need to get them effective. But when your company is potentially facing having to furlough people or freeze hiring, and you can point to something and be like, hey, maybe let's, save this $5,000 a month, right? If you do 3 or 4 of those improvements, that pays for a developer, right? So I think that's kind of the thing of people care about it when they know that it matters to the business, where it matters to the users.
Yeah, very similar to that we had Iris from Farfetch on talking about exactly the same sort of things, that she'd gone through the same ideas of getting people that information visible so that people can care about it, making it easy access, that democratization. It feels like that is kind of becoming that superpower if you can make that available.
Yeah, and also making the things that used to take, wizards to make them accessible to ordinary engineers. So this has been a fun little journey. On a past o11ycast, we had, I believe, the folks from Polar Signals on, right, talking about profiling. And profiling is one of those things that I think is severely underrated because for a long time, it's only been accessible to, the likes of Brendan Gregg. Like Brendan Gregg is awesome and there's only one of him in the world. And how do we ensure that people who are not, performance engineers with a capital P and a capital E, right? Like how do we make sure that developers have access to profiling so that they can see in their IDE, what lines of code are the most expensive, right? I think that kind of making accessible of the performance data makes people make the right decisions because people aren't going seeking out to do a bad job or waste CPU. They just don't know what they don't know.
And they know that spending a ton of time optimizing every line is wrong.
Yes, exactly. Right. Like this is why, when I'm looking at the full stack, right, like I start from top to bottom, right? I look at the biggest wasters and I figure out how can I optimize the biggest waste lines of code in the biggest wasters. But if you're owning your individual service, it's just a lot easier if you kind of tidy up as you go because it means that you have a lot more context as to what is this doing? Is this supposed to be expensive than I do?
Oh, okay. So if a team can look at the CPU usage that's tagged as their services and see where it's highest they have context and they're able to improve that a lot faster without zooming all the way out to the entire company.
Yeah, exactly. It's not necessarily, you should spend 5 hours optimizing this so much as if you see something pop up and it's something that's quick for you to fix, you may as well do it. But the challenge with profiling, I think, has been that, number one, it's been hard to use. Number two, it's been hard to figure out where to apply it. And then number three, I think it's kind of the difference between, hey, we found a bunch of all these technical debt things, right, where we're wasting 30% of the CPU on this job. Once you get rid of those obvious glaring things, you're suddenly into kind of trudging through 0.5%, 1% improvements and having to do a whole bunch of them to kind of make up that 10 or 20 or 30% performance change. There are diminishing returns because a lot of things people just don't fix until they have visibility. As soon as they have visibility, they fix them. So the classic example that I use for this is inside of Honeycomb's services, we have our ingest service, our beloved Shepherd. And they shepherd ingest service for a long time, for many, many years, because again, like this didn't matter originally. It was, a $5,000 a month service, whatever, right? Like this $5,000 a month service was wasting 30% of its time rebuilding the HTTP routing table, right? Like it had a mux that was saying, for this path, for this regex of paths, route it to this particular function. And instead of kind of storing a copy of that on startup, for every request, it was initializing a new multiplexer, right? And it was spending 30% of its CPU time doing that. And no one realized that it was doing that, right? Like it was an oversight and it didn't matter much initially until it did. So we fixed that, of course, as soon as we saw it. And then we stopped having those, right? Like we ran out of 30% improvements to make.
Mm-hmm.
I think depending upon, who's on your team, right? Like it may really, really vary what threshold the kinds of severities of things that you're fixing are. Because it may take someone more time to dig into that 1 or 2% improvement, and it's only a 1 or 2% improvement.
Right. But 1 or 2% of what? And how does your salary compare to that?
How does your salary compare, and how does it compare to the other things that you could be working on?
Right.
The other thing I think is missed in these debates is the idea that it might look like a real improvement when you look at it locally. So, that idea of, I'll look through this code. This function here is really inefficient. I'm going to spend a load of time fixing this particular function. But unless you know that that's something that's used in production at scale, that particular function is a real problem, then you can spend a load of time saying, I've saved 17 seconds. This function was taking 17 seconds, but it's only used once a day. So it's not actually a problem. So knowing something is a problem in production versus it looks like it's a problem because I've seen the code, I think people tend to not see those two as the same thing. You need to actually look at both of them and see, is this a real problem?
Yeah, and people sometimes still complain to me about, OpenTelemetry tracers add, 1% overhead or whatever to my process. I'm like, what are you not discovering because you failed to invest 1%, at most 1% of your CPU time on OTel, right? And it may be that you are optimizing the wrong things, right? Like that you are failing to find that 5 or 10% regression or finding that one function that's very expensive that's captured by a SAN, right? That you really should consider investing in visibility so that you have the data to work with, even if it costs a little bit of performance.
Right, because it's that 1%, if that, overhead of telemetry to give you the observability to find that 30% improvements.
The 30% improvements and then the 5% and the 2% improvements after that. And there will be many, right? And they'll continue to crop up continuously.
Right, because maybe you get down to 1.5% improvements and then you stop, but keep an eye on it for the next 5 or 10 or 30% to crop up.
Yeah.
Because we will all introduce those problems. The code's constantly changing.
That is our job.
We will change something. I always equate it to if you've got a dog and you tickle it behind its ear and all of a sudden its leg starts waggling. Those are the systems that we have these days where we'll make a change in the front end. And all of a sudden, the back end will be like, I've made this change in the front end. It now makes 3 more calls and it makes it so much more efficient. And then all of a sudden, the back end is like, the graphs are going like a sawtooth everywhere. And you're like, I've broken something elsewhere. I didn't know that was going to, you didn't want me to call all 4 of them. Oh, sorry.
Right, exactly. And that is another area where, when you're performance tweaking, you try not to bring production down, right? Like you try to still maintain your service level objectives and also have better utilization, right? So, availability is job one.
Yeah, don't break production, I mean, rule one is don't die. Rule two, don't break production. I'm happy with that priority scale there.
Or at least don't break production for too long, right? Like, it's okay to break production, just roll it back.
Whereas rule one, don't die ever. Don't just die for a little bit. Just don't die.
Unless you're a Kubernetes pod, in which case, whatever, you'll get restarted.
That's suspended animation, right? You get brought back.
Those lambdas are really good at it. Hey, Liz, got any stories from your recent work about this?
Yeah, so the fun one that I've done recently has been wiring up the OTel collectors to emit tagged data of every pod on every node type running in our fleet.
Wait, what kind of data?
The pod utilization data.
Okay.
Like how much CPU is it using, how much memory is it using, and how much is it wasting? How much of the reserved capacity is not in use because you said you needed it and then you weren't actually using it.
For pods that say they need 2 CPUs
and they're actually using 0.5 CPUs or whatever. So I've set up Honeycomb derived columns to basically emit on a per pod basis how much wasted CPU there is. And that's made it a lot faster to drill down and figure out which services should I be investigating next, which service should I make auto scale. And it's uncovered things like, hey, like this service that we thought a while ago had a bug that meant that we couldn't run more than one partition worth of workload on one Kubernetes pod. We should maybe look at revisiting that assumption because now this is suddenly costing a lot of money, right? This is preventing us from scaling down at night. It's resulting in very abysmally low utilization because we are running the same amount of CPU, one pod for each partition, all day, all night, regardless of day of week, regardless of time of day. So that kind of looking at the dollars and cents cost of it was like, okay, this has now become expensive enough. We've added more partitions. Like, we really need to look at auto-scaling this. Like, we need to look at the possibility of running multiple partitions of work on the same pod so that we can scale in and out the number of pods rather than fix the number of pods equals the number of partitions. So it was really, really gratifying to make that change, to kind of validate that the bug that we were seeing before no longer manifested and that we could scale this in and out. And then suddenly you could see that the amount of wasted CPU, the amount of wasted RAM dropped to like a tenth of what it was before. So that was kind of one really, really fun, I like charts, I like graphs, like I like seeing the numbers go down. And that gave me the ammunition to go to the team and say, this is something that's worth investing in because here's how much it's costing us.
Okay.
And this is, how long it was since we last revisited this.
So at some point, we saved developer effort. It was too hard to fix. Maybe it was an underlying library bug.
It was an underlying library bug, yeah. It was an underlying library bug. And at the time, the developer time needed to fix it was not worth the amount of extra CPU we were spending on it. But the library got fixed and we added more partitions, which meant we had to scale this up and keep it scaled up all the time.
And this is a thing where we had to revisit a trade-off where the consequences had changed.
Yeah, that we'd made like 2.5 years ago, yeah. I went and dug up the pull request that was like, fix this to a fixed size.
Nice. Yeah, that's yet another example of software is never done.
It gets both new bugs and new features.
I heard somebody recently that software is only done when it's done its job in production. You've taken it out, deleted the code. That's when it's done.
Yep. And even then you're left with the data.
The carcass of the code.
The other really fun thing in languages like Java and Go and anything that's garbage collected is there is a resource that you're using whether you realize it or not. Every time you allocate a new object on the heap, you are creating future work for the garbage collector. And developers so often are not aware of this because it just turns up as generic, like time spent doing garbage collection, right? So you kind of have to separately collect, you have to do separate measurements of heap, both in terms of total amount of heap and also in terms of number of allocations to heap. And that winds up being, again, like it's one of those surprising things. You're looking at the service and it's like, wait a second, why is this spending 50% of its time doing garbage collection, right? So I think this is one of those things that it's a pattern, right? Like as soon as you recognize it, you know what to do about it. But if you've never encountered it before, never had to think about garbage collections before, it's like, you're just like, why shouldn't I just allocate this on the heap? And in most cases, it's fine to allocate on the heap. It's only when something is like being done a lot that it starts to matter. And you don't know in advance whether something is going to be done a lot.
Right.
Your code reviewer might help catch it, but why not, right? Like it's one of those things where you have to test in production to find out what the performance characteristics are.
Yeah. Like a lot of our front-end code is littered with use memo, which is a caching functionality in a React render function, which might be called 30 times a second for 30 frames a second or something. I mean, I hope not that many, but it's a lot. And so it avoids allocating a function object on the heap every render. And it also clutters up the code and it's annoying. So there's that. You can save the cognitive load of even knowing what the heap is when you're young until you have some consequences. And if you can measure those consequences, then you know how long you may retain your innocence. I mean, ignorance.
I love the idea that you either die young or live old enough to understand heap allocations.
Right? Like, and I think the thing there that's especially scary for front-end observability or FEO is that those are not your machines, right? Like those are machines that you do not control the instrumentation on, right? You can add your own instrumentation, but you will not necessarily see.
Which is really expensive because it's definitely a different region.
It's definitely a different region. It's right, like it's your customer. It's your customer's computers and cell phones, right? And the most you might get a complaint about is, oh, like this is really slow to load, or Chrome, said, this tab is running slowly and to kill it, right? But until it gets to that point, you can hide a lot of ugliness that way. So it's kind of incumbent on you to be economical with your customers, phone's battery life, right? But if you don't know what's going on, you have no idea that this is happening. You have no idea if you introduce a regression. So how can you get better visibility into that so that, I talked earlier about saving dollars. I talked earlier about, saving developer time and, enabling developers to keep their jobs. But also, let's maybe save the planner a little bit. That's been my side quest for a while with talking about Graviton chips, talking about performance engineering. Like every milliwatt of power that you draw, right? Like that's something that needs to be generated. Like we got to start thinking about that.
Yeah. So cheaper, faster, better for the planet.
Yeah, it's just been hard because people haven't had the right signals, people haven't had access to the signals, and now we're starting to kind of crack that, I think. I think the incentives are much more in place for people to start looking at that more seriously.
And observability has some overhead, both in developer time and in CPU and other costs. But it gives you a hope of improving the right thing now.
Yeah.
Great. I think that's a good place to wrap up. Liz, where can people find out more?
You can find more on the Honeycomb blog in general. That's where you'll find a lot of the research and writing that I do.
Honeycomb.io/blog.
That's all we have time for today. If you're interested in being a guest on the show, or if you would like to suggest a topic, find us on Twitter at o11ycast. That's o11ycast. o11ycast is brought to you by Heavybit, the leading investor in developer-first startups. To learn more about Heavybit, visit heavybit.com.